So now let's address a situation that's slightly more complicated than the last two examples. And this is when the force that's being applied to our particle with mass m along this straight line is a function of the position. So it's a position-dependent force, which means that our f sub x is a function of x. And so this means that when we apply Newton's second law, our equation of motion for the acceleration x double dot is equal to f sub x as a function of x, we need to be explicit about that now, is divided by the mass m of the particle. Now, in the prior examples, we've integrated both sides by time. But if we try to apply that mindset here, then we run into problems. I mean, certainly we can integrate the left side with respect to time. We've done that several times. But the problem that we have is here. F of x over m isn't constant any longer, but instead it's a function of x. And remember, x, being our coordinate, is implicitly a function of time. So that means that time is buried within this expression because it's a function of x. So when we stack these dependencies together, the ability to integrate directly with respect to time is something that we lose, and so that means we need to take an alternative approach that considers that this side is dependent upon position, which is implicitly dependent upon time. So what we do is we separate our variables differently. So instead of using time, we're going to pick up on the fact that the right-hand side is a function of x. So first thing what we're going to do is we're going to multiply both sides by dx. So it's x double dot dx is equal to our expression as a function of x dx. Now notice here what we've done is we've introduced the correct integrating variable on the right hand side because it's a function of x, but now we have mismatched variables on the left hand side. Our integrating variable dx doesn't match our expression, which is x double dot. So let's manipulate this variable, x double dot, to get it into a form that is useful for us. We know that x double dot is equal to dx dot dt. So let's make this substitution into this expression, and we'll get dx dot dt, and we're keeping our dx, so we still have mismatched variables here. It's a dx and an x dot, and then we're maintaining the same right hand side. And then recognize here that we have dx dt when we combine these two expressions together. And so now we can substitute dx dt is equal to x dot into the left hand side, which now gives us x dot dx dot is equal to the same right hand side, which we started out with something that was already compatible with an expression that we can calculate. And so now we have the right form in which we can apply our integrals, and so recognize here that we're integrating with different integrating variables on each side. The left hand side is integrating variables x dot, the right hand side is x, and so that's how we want it to be. We apply our boundary conditions, which in this case are simply we're integrating from time 1 to time 2. Remember, all this is implicit in the variables now. So our boundary conditions on the left hand side are x dot at time 1 to x dot at time 2, the speed at time 1, speed at time 2, and on the right hand side it's the position at time 1 to the position at time 2. We work out the integrals, in which we get the expression x dot squared over 2, and then here are our boundary conditions. On the right hand side, we have to leave this integral the same because this function, for the force as a function of x, isn't explicitly defined. Otherwise we could just calculate that integral and apply those boundary conditions. And then, after applying the fundamental theorem of calculus to the left hand side and rearranging, we get that x dot squared at time 2 minus x dot squared at time 1 is equal to 2 multiplied times the integral on the boundary conditions of position from time 1 to time 2 and within the integral is our function of x over m dx. And in the book, they make the notation more general and call this speed v. So it's the speed v at time 2 squared is equal to the speed at time 1 squared. So we're starting with an initial speed on the right-hand side now. And then we have 2 multiplied times this integral, and then we substituted the force as a function of position divided by mass with the expression a as a function of x. And so this expression relates the speed, or the scalar velocity, directly to the position when this quantity ax is known. Now, even though this example was a little bit more complicated than the previous examples, we still had the same process. We applied the mechanics laws, Newton's second law, and we came up with an equation of motion and then worked down through the math to then be able to relate the speed with the position in this situation. So the heart of this is that we have equations of motion. They're second order differential equations that we solve to find the state, and sometimes we have to be clever to solve these. So we've got a bag of tricks that we have from differential equations to solve them when it's possible to solve them, and then when we can't solve things directly, we'll solve them numerically.